This video is after periodic trends, basically be like on covalent compounds, drawing them, telling shapes, telling if they're polar or non-polar, those types of things. So this is about page 5 of your notes. So quick review here. Ionic bond would be a metal and a non-metal, and there's no sharing of electrons. So think about that briefly. Think about like NaCl. Na's got one valence electron. Chlorine's got 7 valence electrons. So metals really want to get rid of electrons. Non-metals really want to gain electrons. That's supposed to be electron. So sodium wants to get rid of one, chlorine wants to gain one. Sodium is actually giving its electron to chlorine when it makes that ionic bond. So there's no sharing of electrons there. Sodium and chlorine are not sharing electrons. Sodium is giving electrons. So makes it a very, very polar molecule, if you even want to call it that. Ionic compounds oftentimes are even classified as that, but a very negative, very positive end to that molecule. Just some things about ionic compounds: high melting points, boiling points. They do not conduct electricity as liquid, but they do as liquids, not as solids. They do as liquids and when dissolved in water. Remember, they dissociate into ions. Covalent bonds, sharing electrons. Okay, and they are called molecular compounds. Covalent compounds are called molecular compounds. Remember, they do not dissociate in water. They stay together as molecules. Even if they dissolve, they still stay together as molecules. It's always 2 nonmetals, whereas up here, 2 or more nonmetals. Up there, it's always a metal with a nonmetal. 2 types of covalent bonds. You can have a nonpolar bond or a polar bond. Nonpolar, polar bond. We'll talk about those as we go on. All right. Most of this is going to be on just drawing them. So we're going to need to be able to draw a compound, tell the electron geometry and molecular geometry. So there will be a shape sheet that you will look at for that. Sheet's got shapes on it. Tell if the bond is ionic, polar, or nonpolar. Tell if the molecule itself as a whole is polar or nonpolar. Tell the hybridization of the central element, which we won't always do, but sometimes we will. And then tell how many sigma and pi bonds are present is another thing which we may or may not get to here, probably not in this video. So first thing, these compounds are ionic compounds. I know that because it's always a metal with a non-metal. Metal, non-metal, metal, non-metal. So these are all ionic. So I draw these a little bit differently than I do covalent compounds. So we're trying to draw what's called the Lewis structure. So we're going to do our dots, our Lewis dots, draw our bonds in. So potassium, 1 valence electron. It wants to get rid of that electron. Oxygen, 6 valence electrons. Really wants to gain 2 electrons. So move this forward a little bit. There you go. Ionic bond. Potassium is giving an electron to that. There's always 2 electrons involved in a bond. I don't care if it's ionic, covalent. Always 2 electrons involved in a bond. So I usually just go like that. There's a bond. Potassium got rid of its electron. Oxygen gained 1. Oxygen still wants to gain 1 more electron, so we need another potassium. Right there. So these are ionic bonds. So that means they're not considered polar or nonpolar. Single bonds are sigma bonds. We'll get to that later. Pi bonds are single bonds are sigma bonds. Double bonds are a sigma bond and a pi bond together, which we'll get to. Hybridization we're going to talk about. I will show you shapes here in a minute, okay? I will tell you this. Around the central element, these electrons want to be as far away from each other as possible. They want to be as far as they can away from each other. If we're doing aluminum and nitrogen, aluminum has 1, 2, 3 valence electrons. Nitrogen's got 1, 2, 3, 4, 5 valence electrons. Well, aluminum wants to get rid of 3 electrons. Nitrogen wants to gain 3. So we're going to go bond, bond, bond. Again, these are ionic bonds. Shape is linear. This shape over here was bent. Okay, I'll explain the shapes here in a little bit, but this shape was bent. Should put that on there. I'll do one more here. Iron 3 sulfide. So iron, if you see a Roman numeral 3, that means it has 3 valence electrons. Sulfur, has 6 valence. So sulfur wants to gain 2. Well, iron can give it 1, 2. So we got 2 electrons involved in bond. Again, it's still an ionic bond. Iron is giving away its electrons, sulfur is taking them. Well, iron has another one to give, so let's add in another sulfur. This sulfur can take that electron. It still needs to gain 1 more, so put in another iron, which has 3 valence electrons. Iron can give sulfur 1 there. So our sulfur has gained. Nonmetals will always have 8 electrons around them when you're dead. Nonmetals always 8 around them. So 1, 2, 3, 4, 5, 6, 7, 8 bonds count as 2 electrons. So this sulfur's got 8 around it. This sulfur has 2, 4, 6, 8 electrons around it. Okay, these are bonding pairs, unshared pair, unshared pair. We need another sulfur in here. 1, 2, 3, 4, 5, 6 valence. Iron can give, make a bond, and give, make a bond. So notice our metals never have unshared pairs of electrons around them. They're always giving away their electrons. We won't worry about shape there. So there's some ionic compounds. Let me go to a different site here. All right, here's a little bit on molecular geometry and electron geometry. So we're always looking at the central element and things coming off of it. So it's all based on something called VSEPR, valence shell electron pair repulsion. Valence shell electron pair repulsion. In other words, electrons, the 2 electrons in this bond and this bond want to be as far away from each other as they can. So in this case, these 2 electrons and these 2 electrons around the central element are 180 degrees apart. Okay, they're trying to be as far away from each other as they can around the central element. Electrons do not like each other because of the same charge. So whenever you have a central element, bond, no unshared pairs in the central element, it will be linear. Okay, so your molecular geometry is linear. Your electron geometry is linear. If there was an unshared pair of electrons on there, okay, unshared pair. See if I can move this molecule around a little bit. So unshared pair. Now we have electrons. You got 2 electrons there, electrons in this bond, and 2 electrons in that bond. Well, as far as they can be, it would be about 120 degrees that way, 120 that way, and 120 that way. So these electron pairs are 120 degrees apart all the way around. Our electron geometry is called trigonal planar. Okay, our molecular geometry, so our electron geometry would be where our electrons are at, is trigonal planar. Our molecular geometry, the molecule itself, is just bent. The shape of the molecule is just bent. All right. If I take this off, if I take off the lone pair and add a bonded element, so just like before we had electron pair, and we had an unshared pair up here, now we have a shared pair, our bond angle is still 120 between each thing. Still 120 between each. So our electron geometry, electron pair is trigonal planar, and our molecular geometry is trigonal planar. These will be the same whenever there's not an unshared pair in the central element. Your molecular geometry and electron geometry will be the same whenever there's no unshared pairs in the central element. All right. So that's when we got 3 things coming off the central element. Let's say we have 4 things coming off the central element. So you might think 90 degrees would be the bond angle, but 3-dimensionally, it's 109.5 degrees. If you draw it on paper, it looks like 90 degrees, but you can get up to 109.5 degrees right there. This is called tetrahedral for shape. Again, there's 4 electron pairs around the central element, all bonded in there. If one of these was gone and it was replaced with an unshared pair, so let's take one off and replace it with an unshared pair. Take that off, put a lone pair on there. Our bond angle is still about 109.5. It'd actually be just a little bit less than that. Unshared pairs have more repulsion than shared pairs. So our electron geometry has not changed. We still have 1, 2, 3, 4 pairs around the central element. 4 pairs around the central element are always tetrahedral. An unshared pair with 3 bonds is trigonal pyramidal. If I take off another one of these, take off a bond and replace it with the lone pair. So we take off a bond, replace it with a lone pair. Oops, sorry. So we still have 1, 2, 3, 4 electron pairs on central element, so that's still tetrahedral electron geometry, but our molecular geometry is now just bent. The molecule itself is just bent. Right? There's only going to be so many electron geometries. You're going to have a linear, you're going to have trigonal planar, you're going to have tetrahedral, trigonal bipyramidal, and octahedral will be our 5 electron geometries as we're doing this stuff. All right, those are all the ones without expanded octets. We'll get into expanded octets a little bit later. I think I'm going to stop there. I'll make a new video to show how to draw covalent molecules. Okay, how to draw covalent molecules and then tell the shapes from there.